All right, let's go ahead and go over it. So a long time ago, Unit 1, Lesson 20, we learned about parallel lines. And we learned that when we have two angles that are in the same position, right? These are both in the bottom left. Those angles are called corresponding angles. And something that we know about parallel lines is that if I have two lines that are parallel, then corresponding angles are congruent. So I flipped the image around. So if two lines are parallel, then corresponding angles are congruent. Now the great thing about this theorem, this is corresponding angles theorem, is that it also works backwards. If corresponding angles are congruent, then the lines are parallel. Okay, so if you did a proof, you probably referenced this theorem. If you were thinking about what information we would need to know in order to be sure that we have parallel lines, this is a piece of information that we could use. We could show that two angles are going to be congruent, and that'll tell us that those lines are parallel. Okay? So using that as our basis, let's go ahead and do this proof together. Yeah. The very first thing that we're going to do is we're going to label E a new point. We could call it D because we haven't used D yet, but I'll go ahead and call it E. We're going to label a new point E that's somewhere in between P and C. And it doesn't have to be a specific place. I'm just going to pick halfway just because that's a nice, round number, hopefully. All right, so yeah, the distance here from C to P looks like it's 2 centimeters. Okay, so I'm going to put point E right here at 1 centimeter. Okay, so right there. So there's a new point called E. Okay, so step 1. Mark E between P and C. Okay. Step 2 is when we dilate this triangle, when we dilate ABC and we get A prime, B prime, C prime, let's also dilate E prime by the same scale factor. Okay, so if I dilate E prime by a scale factor of 2, the distance from P to E prime was 1 centimeter. So this should be E, not E prime. There we go. The distance from P to E equals 1. Okay? So if I multiply that by a scale factor of 2, then P to E prime is going to be 2 centimeters. So E prime is going to be right there at C. Okay? So I'm going to put E prime right there at C. Okay? So let's go ahead and draw in the lines that pass through P and E. Let's draw in this line. And let's draw in these lines. All right. So the next step of our proof is we have dilated. Okay, so dilate E by the same scale factor. So we want to write this proof so that no matter what the scale factor, that it always works, right? So instead of picking a specific number for the scale factor, I'm going to use a variable, right? So dilate E by scale factor K. I'll just use K for factor. By scale factor K. Okay. So now, what if I dilate E, what does this tell me, right? There's a couple things that I'm going to know about this. First of all, I'm going to know for sure that oh wait, dilate E by scale factor K from center C. We've got to write that first. Okay. So there's a couple things that we know about this dilation. The first is that by the definition of a dilation, we're going to have C and E, are C prime and E prime are both going to be on ray CE. Okay? So I'm going to have C, E prime and C are both on ray CE. Oh, we'll call this, yeah, CE, by the definition of dilation. Then